Good morning, my name's Gian, and today I'm going to talk about how tDCS affects people with major depressive disorder. So what I'm going to talk about today is how tDCS works, what are the physiological mechanisms of major depressive disorder, how tDCS interacts with major depressive disorder, and what are future directions for study. So what is tDCS? tDCS is a non-invasive technique of modulating human brain activity. It uses a small voltage of 1 to 2 milliamps to modify intercellular ion concentration in the cortical tissue. The main components are the anode and the cathode. The anode has a positive charge, which depolarizes the cell membrane, which brings it closer to an action potential. So cells close to the anode require less stimulation to depolarize and cause an action potential. At the cathode, it's got a negative charge, which causes an inhibitory response as it hyperpolarizes the cells, so there is a lower chance of an action potential happening. It's worth noting that it does not cause action potentials, and it's also worth noting that tDCS increases neural plasticity. So tDCS has some after effects. The response does continue after the stimulation. It's thought to be caused by synaptic changes, but it does also cause changes in other cells. Moving on to major depressive disorder, the first thing is the global decrease in activity in the left hemisphere and an increased activity in the right cortex. The second thing is there's a disruption to the hypothalamic pituitary adrenal axis, disruption in the hippocampus, and neurotrophic disruption, specifically BDNF. So starting at the HPA axis, the HPA axis is responsible for the release of glucocorticoids or cortisol in humans. Increased cortisol levels, which come with major depressive disorder, decreases BDNF in the hippocampus and amygdala, which causes cell death. Because the hippocampus has an inhibitory response on the HPA axis then goes on to produce more cortisol, which then causes less BDNF, and it falls into this cycle where more and more cortisol is produced and less BDNF is produced, so people can really get stuck in that headspace. So other effects are reduced plasticity in the amygdala and hippocampus, partially due to decreased BDNF expression. There's a disruption in the hypothalamus and amygdala, which is thought to lead to abnormal hormonal productions for things including orexin and melanin concentrating hormones. Lastly, note that CREB levels are reduced for patients with depression, particularly in the temporal lobe. Moving on to interactions between major depressive disorder and tDCS. Below is a chart showing where the anode and cathode would be placed on a participant. So the goal of this is to put the anode on the left hemisphere and increase its firing, and the cathode on the right hemisphere and decrease its firing to even out the firing to a normal level. So tDCS is also believed to affect subcortical areas such as the hippocampus, and these downstream effects, particularly on the hippocampus, are thought to increase activity in the hippocampus, which restores some of the inhibitory control it has over the HPA axis. Other interactions, because tDCS increases neuroplasticity, it's thought to restore the neuroplasticity in the amygdala and hippocampus. And it's also worth noting that neurotrophic factors other than BDNF are not affected by tDCS. Directions for future research. It'd be really good to see how non-neuron cells are affected by tDCS and how that interacts with major depressive disorder. Comparing the relapse rate of tDCS to other treatments such as antidepressants, and to have a closer look at how hormones and the amygdala are affected by tDCS. Overall, I think it's quite clear that tDCS does a great job of counteracting some of the negative physiological effects of major depressive disorder. Thank you very much for listening.